Okay, so like I said, this is section 4.4, and it is called optimization. I gave you guys the definition for like regular life, but in math, optimization is basically finding what is the maximum or minimum value of some kind of objective function subject to some given constraints. So, for example, what is the maximum number of homework assignments I can complete in a day under the constraint of 9 hours of work time? The answer is much more than I have actually been doing. But just to clarify some terminology, when I say objective function, oh, yikes. That's just whatever we want to maximize or minimize. Okay? So basically, we're going to use what we learned in section 4.2 about finding maximums and minimums to create a solvable system of equations. All right, and basically for this section, it's just going to be a million examples because that is what is the most helpful. So example 1 is all we'll be doing in this video, and I'll post 2 more example videos. This is also going to involve a lot of writing just because these are all word problems, so bear with me. For this one, we are going to have a rancher who has 400 feet of fencing with which to construct. That's dumb grammar. Anyway. The following rectangular corral. Okay, so let me draw the picture really quickly. Basically, they have, this side is a barn, so it's not a fence. And then they've divided the corral into 3 sections. Please assume that that is 90 degrees. And these sides are all the same length. And then this side is a different length. Okay, and the question is, what are the dimensions of the corral that maximize the enclosed area? And also, what is the area of the maximized corral? So, like every word problem, we have things that we care about. We care about that we have 400 feet of fencing. We care about the dimensions of our picture. And we care about what we need to find. So we need to find basically the maximized area and the dimensions that give us that. Okay, so Let's write down what we have and what we want to find. We have, based on our picture, that we have 400 feet of fencing, and we need all of our different lengths of fence to equal that. So x plus x plus x plus x and y, which we could rewrite as 4x plus y. We want to maximize a equals xy. That's our area. Okay? So to maximize a, or I guess to find the maximal a, we need to take a derivative. So we need a to be in terms of one of our values, either x or y. I'm going to choose x. This is the letter 1. Number 1? Anyway. Okay, so we can do that because we have 400 is equal to 4x plus y, which gives us y is equal to 400 minus 4x. So we can rewrite the area equals xy as x times 400 minus 4x, because we're just taking this, which we solved for y, and plugging it into our value of y here. Okay, so if we rewrite that, that gives us 400x minus 4x squared. So now we can take our derivative. We have a prime of x is equal to 400 minus 8x. And we're going to set that equal to 0 and solve for x. So we have 400 minus 8x is equal to 0 when x is equal to 50. So we know that this is a critical value. All right. So now we need to test to make sure that it's a maximum. So if I take, we're going to use the second derivative test. The second derivative of our area is just a negative 8. The second derivative of 50, therefore, is just a negative 8 because the second derivative doesn't depend on x, right? So whatever x I plug in, I'm going to get a negative 8. Negative 8 is less than 0, which we know from the second derivative test means this is a local maximum. Okay, so to answer our question, we had to figure out the dimensions, which are x and y, and the area. So we know dimensions. We know x needs to equal 50 feet, and we need to solve for what y needs to be. So we know that 400 is equal to 4 times our x, or 50 in this case, plus y, which if we solve gives us y equals 200. So our dimensions are x equals 50 feet and y equals 200 feet. And then we need the area. And we know that the area is just our x times our y And 50 times 200 is 10,000, and that'll be feet squared. Okay, and that's the answer. If you notice, this will actually create square sections of our corral here, and that happens to always be true. When you're trying to maximize the area of a rectangle, you should always get squares unless there's another weird constraint put on it. For example, maybe one side has to be twice as long as another or something like that. Yeah, so that's your guys' first example to an optimization problem. I did want to give you guys a kind of cheat sheet from, let me see if this works. Yeah, there we go. Okay, a cheat sheet from section 4.2. So that's what this guy is. Let me see if I can make that reasonable. So, if you guys want to write this down on your cheat sheet, it is kind of helpful to summarize what happened in section 4.2. It's just a nice reference guide. I like it if you're a visual person, and I thought I would provide that to you guys, so feel free to pause this and copy it down. All right, see you guys in the next example video.